Right, hell yeah. So we have torsion, and this book is Material Mechanics. This is James Gear. So hell yeah. And we're going to be going over the proofs, the derivations. Oh man, this is just really hard to actually dial in a page. Let's see what... Okay, there we go. All right, hell yeah. And so we did the introduction in a video. And then the other thing that we did is we kind of went over how a cylinder, a shaft, you just imagine this is made out of metal. We're going to fix it or weld it to one end. Then we're going to torque on the other end. That's the same thing as torquing on both ends. And what we get is a rotation, a twisting, a uniform twist, as long as the material is, all the same. And then we derived an equation, based on that. And the twist doesn't have to be linear. It could be some sort of function. But hell yeah, in this case, this is going to be the twist that happens. And the equation that we derived is the fact that, hey, this is made out of material. What we know about material mechanics is that, and hell yeah, we got our, if we have like two, I'm just going to say, these circles, for me, I'm just going to say they're like iron atoms. And we have some sort of chemistry going on. Usually it's electro, and I'm just gonna bum up that, but what, electrostatic, You have negative charges floating around, and then you have positive charges. I don't know, whatever. But anyway, so you have some sort of connection between atoms. What I'm going to say, though, the fundamentals of this is that we can take those two and pull them apart. But we can only do that so far until that bond breaks, if this is a bond. The other thing that's interesting is that, these are all the, I think, from the chemistry perspective, all the protons and masses, protons and neutrons are here, and then you have your electrons on the outside. If I put forces and crush these in, or put compression, also, I can only squeeze them in so far before they become unstable, and you get like some sort of break again. Even though if you put these, in a cylinder and rammed them together, you could put infinite amount of compression, but it's just the fact that when they're in a lattice structure, and we put compression on there, hell yeah, then these are unstable, and they do kind of shift. Now, what happens is, like, you get voids, and then when you actually push on these things, there's a tendency for these molecules to fill in the voids. Same thing if you pull these apart. If you pull these apart, there's a tendency for one of these to actually fill in the void, and this whole thing gets thinner. So that's kind of material mechanics in a nutshell. And then I talk about that if you have two of these atoms, and I just move this one up and this one down, that gets kind of nonsensical, because isn't that just orienting them at an angle? So, I come up with the idea that you at least need 4 of these atoms to actually have a structure that can take an upward force and a downward force like this. But still, this is just going to rotate into, if this is a rectangle, if this is a square shape, it's just going to, if I put a force this way and a force that way, it's just going to spin. And then so shear is applying a force this way, a force that way, which that ultimately makes a moment, a spin, a tendency to spin, and we have to resist that by putting a force this way and a force this way. And I'm going to say that you can only apply a force through the center of mass of these atoms, and so this kind of makes sense. I can grip this atom and pull it that way. I can grip this atom and pull it that way. I can push on this atom right through that center, and I can push on this one right through that center. So these two have a tendency to rotate it that way. These two forces on these two atoms, tendency to rotate. Now we're balanced. And when we do this, we get a diamond shape to occur. These two atoms move up, these 2 atoms move down, we get this diamond shape. Just for this would be considered negative shear because we have a rotation in the counterclockwise. Just know that it's opposite of the right-hand rule. So if I had the diamond shape look like this, where we had these 4, we put a downward force this way, an upward force that way. We would have to balance that by applying a force this way and this way. If we did that, that's the diamond shape. Like the resultant over here is going to be this way, and the resultant over here is going to be at that diagonal. And then we get this diamond shape to form. And so this is what we call shear. And this is what happens when we torque a cylinder. And the easiest representation of this is to imagine that this cylinder is hollow. And so that's going to be a hollow portion. And just imagine that the outside skin of this cylinder is these iron atoms. So the inside is hollow. There's just nothing inside. The outside is these. And it's very useful to imagine big cylinders, big as you can imagine, just because kind of like, you know how the Earth appears flat. This cylinder on the surface now is made up of these iron atoms, you know, and I think steel is a pretty useful one, and they go around in a circle, and then helium, and then you have this ring of them, and then for the derivation, it's useful to think of like, hey, this is a disk of iron atoms, in, you know, somewhere at a distance x, and this is just kind of a review of the last video. And see if we can do it fairly fast. On this face, hey, you got, you know, just all these iron atoms. Oh, but we said it's hollow. So hell yeah, you just have a ring of iron atoms. On this end over here, you have a ring of iron atoms. And all along here, you just have ring after ring of iron atoms. And so right here, these two are butted up against another ring of iron atoms. And so right there, there's going to be 2 rings. And so just kind of do that. And for our derivation, hey, I can say those 2 rings are a distance dx. That seems like a pretty small distance, even though we designate dx to be an infinitesimally small distance. But I think getting down to a couple layers of iron atoms, I think that's small enough. And it's very useful. I like to think of that. I don't like to think of something so infinitesimally small it almost doesn't exist, but does exist. That is bizarre to me. So even though this is an approximation, I like to always, when using calculus terms, to understand that we are, if I give this any sort of dimension, I'm getting an approximation. And as I make this dimension smaller and smaller, I get a better approximation. But at a certain point, you just don't care. It's small enough. And we get a pretty good approximation. Okay, so when I take this cylinder over here, and then, well, let's talk about this right here. Because this sign, the 2 double arrows, indicate a twist. We're applying a moment, and the T is for torque. It could be T, it could be M for moment, or it could be C for a couple. And hell yeah. And we use the right-hand rule. So my thumb is going to be this direction, and then I got 4 fingers. And this is my palm. And so when I sweep my fingers are going this direction. So put your thumb in that direction, sweep your fingers, and that's going to be sweeping out an arc this way. And that's going to be how this thing twists. So if I draw a straight line on here, after I twist it, that straight line is going to be, it looks like it's going to be at a diagonal. But we do call this a helix, because with materials that are long, and let's say they're just, the radiuses and diameters are small, I might be able to twist this a full 360. So then this line is now going down and around in a helix and back up to the top to its starting point. And so, And that can easily happen. And then with material properties, I can let go, and guess what? That whole cylinder goes right back to the same, that line goes perfectly straight. So that is kind of an interesting property of material mechanics, is that if I have two iron atoms and I pull them apart, I can pull them apart not very much, 0.2% if it's steel. So, you know what I mean? If this is 1,000 millimeters, I can pull it 2 millimeters if this is 1,000. And then let go, and then the two iron atoms will go back, or I mean, whatever your thing is made out of steel will go back to the original length. If I stretch it more, if this is a 1 meter or 1,000 millimeters, stretch it more, it's going to be permanently deformed. If I stretch it 3 millimeters, it's not going to stay at 3. It's going to go back at least 2. You know what I mean? If I can stretch it 2, that's the elasticity of it. And so if I stretch it 3, it's going to go back to being stretched out by 1 millimeter. So that's kind of how that process works. All right, and the same, and that's just for pulling on something linearly. We talked about crushing something in. If it's 1,000, I can crush it in 2. If I crush it in 3, it's going to rebound 2 and be crushed in a distance of 1. Now, what happens if I have these 4 in a square? Well, it's we use a different property, but it should be noted that this shear is still related to axial tension and axial compression. We just get axial tension and axial compression to happen in 2 different locations. So, like I said, if I have 2 of these iron atoms, it's nonsensical to say, can I move this one up just a fraction? Because it seems like you're just rotating this thing, and that would take no force at all. You could easily do that. You could just rotate this at any orientation you wanted. But if I have these 2, if I have these 4, and I want to say, hey, I want to move these 2 atoms up to here, to a new location, while keeping these 2 fixed. You know what I mean? That's not nonsensical, because back here, if I have this one fixed, and then my goal is just to move this one up a little bit, well, that seems like it's not going to, it seems like you just rotated it. So if I fix both of these in place and then move these 2 up, now we have something. And the reason we have something, so I'm going to say this is the new location of that one and that one, is because when we have these 4 in a line like this, well, we like these 2, obey that axial principle of like, hey, I can only pull it apart so much before we get a breakage. So these 2 can get pulled apart. These 2 can get pulled apart axially, and that, you know what I mean? These 2 can get pulled apart axially this way. These 2 can get pulled apart axially that way. But look at this diagonal. These 2 can get pulled apart axially this way and that way. Same with this one. This one and this one can get pulled apart axially that way. And we can only pull those apart a percentage of 0.2% if it's steel. The second those get pulled apart that much, just think breakage. You know what I mean? Well, we get permanently deformation. You know, we get a bent tool, but the second things start getting bent, like think you're gonna kill someone, you're gonna lose your job and stuff. And you know, I always bring that up because materials are strong through their linear range. We design a ton of things, like 50% inside that linear range. If this is a linear range, and then here's where things get plastic, you do get some more juice out of it. Let's design it right there. So this is where most of the strength of materials come from. You only eke out a little bit of strength after that, just because things deform and might get skinnier. I mean, sure, it gets twice as strong, but you just get twice as skinny, you know what I mean, kind of. Or actually, that's exactly what happens. Okay, so hell yeah. So when we move these 2 up, look at these. These 2 got farther apart. So now that distance used to be here, and now it's this 0.2%. If that gets into that 0.2% range, that's its limit. If it goes any farther, you can't go no farther. People die, let's say. Okay, and then here, if I move this one to this location, these two used to be center on center here, and now they're there to there. So these two actually get crunched in, and I can only move those in by 0.2 before, you know, the molecules fill in the voids and we start plastically deforming this, and it gets bent. And just think bent means you kill people. So anyway, so hell yeah. So that's how we determine how much we can make this square of 4 iron molecules to be in this diamond shape. It's solely based on this length right here. If things cannot take tension worth a darn, this length is extremely important. It's like chalk. Chalk can take this compression all day, but chalk cannot be pulled in tension. The second you do get whatever number, you know, whatever percentage, it's going to be different for all material. 0.2% of this length is for steel, but for chalk, well, you know, whatever, it's a number. And once that gets to be that distance, it used to be, the centers used to be closer, and now it got that far apart, hey, that chalk breaks. And that chalk breaks between this bond of that one. The second that one breaks, the others in that same orientation break, and you get breakage along that diagonal. That diagonal will have a helical, anyway, so that's for chalk. And you know what I mean? Sometimes for ductile materials, hey, you moved it this far, like we talked about, you got more than 0.2%. Let's say you went up to that 0.3%. Well, cool, it's going to rebound, but it's going to be bent a little bit. So now your square is not square, and you have a permanently shaped diamond. And so we want to know that. We want to know the max. And so what we do for this square shape is that, hey, like what we, how do you say that? What we use to observe whether this thing gets, so if I have a steel bar that's 1 meter, I can visualize it lengthening 2 millimeters, and that's the limit. If it's 1 meter here, and then I shrink it into there by 2 millimeters, that's the limit on compression. Same thing for this. So if these two lengths get to be, you know, that 0.2%, then that's my limit. So the lengths used to be here, and now the lengths are there. This used to be there, and now the lengths are there. Those two parameters, but those are kind of mathematically, like there's a proof for that. But then the question is, well, what's this angle? I mean, we are going to have this diamond shape. So if we do have this, what's this angle going to happen? And that angle is what we call gamma. And I'm going to say it again. I have a very hard time relating this gamma as an angle. This seems like an angle to me. This seems like an angle to me. And it's just very difficult for me to throw this into my game. This seems like density. You know what I mean? And maybe I need to look up my Greek letters, because isn't this the same as that? You know what I mean? They just have it kind of drawn like, I don't know, I'll have to look that up. Sometimes the Greek letters surprise me, and that is a different letter than that. But I'm just going to call this gamma. Again, I need to look that up. But yeah, that's an angle. And that's what we're going to be looking at. Okay, cool. So for any material, I can only have a max number for this angle. And that is because I can only have a max number for this length that used to be here and now it's here. And this length and compression that used to be here and now it's crunched in. And so, so yeah, the angle that forms, and if you do the math, I mean, it's cool for steel because steel is 0.002, and that's going to be the factor. You multiply that by the length, let's say the length is 1,000, and you get 2 millimeters. So that's that 0.2%. Take this and move the decimal place 2, and you get 0.2%. 0.2% of the length, if it's 1,000 millimeters, 0.2% is 2 millimeters, and that's what you can lengthen or compress steel. This number, this angle, comes out to be 0.004. And I think, and now we're going to, I don't want to bum up this picture, because when we have this cylinder, we draw this shape right here, and when we apply this torque, that's why we use the right hand rule. We're twisting this face this way. We're welding this face to the wall, so that's the same thing as this face getting twisted that way. So right here, we're going to have an upward movement of that and a downward movement of that. This would cause this thing to move in a clockwise way, and that's going to be what we consider positive shear. So even though that I've been drawing this thing in this direction, this is associated with negative shear. Even though just from a visual picture, it's kind of easy to draw, because if this is my XY axis, everything stays in this whatever the hell quadrant this is in the XY. I forget if this is your quadrant. Is this yeah, this is one. The first quadrant. This is the first, second, third, fourth. So if I have an XY, even though this is negative shear, it's probably the easiest one to just visualize. But hell yeah. Okay, but positive shear is going to be done like this, where you have that square shape turn into a diamond like that. You know what I mean? And now where the hell do you put your XY axes? But hell yeah. But that is the core principle, or the foundation of why we can analyze and do a proof of a cylinder in torsion. And what's holding that torsion back is these molecules in pure shear. Well, what they're going to say for the derivation is that at no point does this length crunch in. You don't get any axial compression. At no point does this thing lengthen, which could be different than just having a loose spring. If I take a loose spring and then twist it this way and I twist it that way, hey, it seems like the length would change. But for this, because the molecules can only move so far, you know, I mean, with materials, that linear range is for like steel and stuff, is very small changes in length. It's very small angle changes. 0.004 radians isn't very much. And so, you know, so that's one of the principles or the foundations of these proofs of torsion, is that this length does not change, you know, appreciably or noticeably or at all, or you know, we don't take that into consideration whatsoever, and because it just doesn't change. There you go. Cool. All right, and then so we get this value of 0.004 radians. Can I start erasing stuff? Oh, I'd have to erase like but yeah. Let's just get some. I just want to get a little bit of clear. So if I have this square shape, and I'm wanting to, you know what I mean? Because if I have a bar, I always imagine 1,000 millimeter bar. That's a 1 meter bar, and I can stretch it 2 millimeters. So how do I get a representation of this 0.004 radians? You know what I mean? It seems difficult to actually put that into perspective. So what I do, and then, you know, because this thing's going to make this diamond shape. And when it makes that diamond shape, this is the angle that forms right there. And that angle is 0.004 radians. So what I say is this square shape, you know, is not for iron atoms. I'm going to say it's a 1 meter by 1 meter chunk of steel. And if I do that, this is 1,000 millimeters. And what we know, and for the proofs, is we know that this angle is very small. 0.004 radians is really small. And it is good to actually always put some bearing on that, you know what I mean? Because that's, you know, we know a circle is 360 degrees. We're familiar with that. This is 90, this is 90, 90, and 90. That's 360. Radians is another battle. So anytime you are working in radians and you're not just 100% solid, draw a circle, draw the radius, pretend like you're cutting a string, that length, and then start draping it around. And use your noggin. How far are you going to get? You're going to get to about there. Okay, and then this should rattle your brain to be like, oh yeah, I can get about 60 degrees. I remember that, but it's 57, not quite 60. And if I go 60, and then go 120, and then go 180, and then go... you know, I'm not going to do the math because I'm bad at it. But hell yeah, 180 plus 60. Don't know it, but that's but I do know what 200 plus 60 is. That's 260 minus 20 is 240. So we go 240. Did I get that right? 240, 300, 360. Hell yeah. That's if this was 60 degrees. And then I totally forgot that we're designating this angle as 1 radian. So that's what we're saying 1 radian is. It's if you cut a radius, a string, and then draped it around the circle, you would get to 60 degrees. And about. But if you cut, you could cut 6 of these, and you'd get to about here, but you'd have a little bit more. You'd have to cut another 0.28. And so we get 6.28. And it is very good to write down the 6.28 and then just be like, oh yeah, half of that's 3.14. See how if you half 6, you get 3, half 2, you get 1, and half 8, you get 4. That's also something very good to do, is because, you know, this is 3.141. So like even that digit, that third decimal, is like a little bit irrelevant. And then so like, hey, 3.14 and 6.28, kind of a nice little perfect pair. And 6.28 we call 2 pi. So hell yeah. But 2 pi, it no longer becomes like an integer number, or even people paying attention to the fact that 2 pi starts with like the 6 digit. You know what I mean? That's 6. 6 what? 6 radians. So a circle has an angle of 6 of these, you know, individual angle of 1 radian is about that angle, and you got about 6 of them in a circle. Okay, so 1 radian is to there. What is 0.004? Well, there's a half a radian. A tenth of a radian is about there, and that's a tenth. That would be 0.1 radian. Okay, so hell yeah. How about... You know what I mean? How about a tenth of that? I can't even see it on my computer screen, but that's 0.01. Hey, 0.004. I'm just going to round this the hell up to 0.01 because we can't even see it anymore. But that's what we're talking about. This angle is hella small. And anytime you're dealing with small angles and stuff, it is also good. Well, we'll get a stylus at some point so we can make better videos. I'm just doing this to figure out how the hell to teach and learn and just kind of have a good time. You know what I mean? But yeah, this is such a good one to do. Because if I have like a 30-degree angle, that's not even 30 degrees. But what happens, they'll throw the unit triangle on you, where this is a distance of 1, the hypotenuse is 1. Make it 100, make it 10. Do anything besides 1, though. You know what I mean? Because if this is 100, hey, check it out. And then start divvying this up into halves and quarters. And look at this. This length is about half. Not quite, but maybe this, just guess, this is about 45. And guess what this length is? Well, just roll it up into here, and maybe it's like 90. Maybe it's like 92. So what we're getting at is this number is very similar to this number. And this number can be substantial, even though we have a small angle. So now let's make this angle even smaller. Let's half it. This becomes about 20. This really ramps up too close to 100. Let's start halving that again, and we get to there. This, still we get 10. This just becomes 100. Like, this length is the same as that length. And what we get is this... oh, how could I explain this? Or, yeah, let's see. Yeah, why does that work out? I totally forget why, oh. No, we can do this. Yeah, it shouldn't be that crazy. But why, when we do small angles, can we just use that angle in radians to equal the arc length? It's because this. So we're going to draw, and then this is important. I need to get better at this every time. If I draw this radius in, and I draw this 60 degrees, what we have here is this is the angle, this is the arc length, and we're going to call that S. And then if this is the angle in radians, and I guess I'm going to try to use this gamma. You know, don't want to. Doesn't look like an angle to me, but that's the angle gamma. And then, and we're going to drop down a right triangle. And what do we know about right triangles? This is the sine component. This would be sine gamma. This is the cosine component, this length right here. This is cosine gamma. And we just said that this is the radius right here. And if I take this length right here and sweep it out to here, this arc length is also the radius. Okay? I mean, do you buy that? Hell yeah. And what we're going to say is that this line right here, this curve, is very close to this length. Like, even at a 60 degrees, it's like, well, I mean, looks like we got some error, because this length, like, yeah, this length is the radius, and this length is, but we only get, at 60 degrees, this length is 0.86, the radius. So it's like right here, this is your radius, this is your hypotenuse. If this is 60, then this is like 85, you know what I mean? I'm sorry, if this radius right here, let's say we say this length is 100, you know what I mean? We're trying to use the unit circle, but just use different values, like 100. This is 86. Okay, so, but that's your approximation. Even at 60 degrees, you can still say that this arc length is equal to the sine of gamma. So that's r, that's the radius, r sine gamma. So that's the mathematical. If this is your hypotenuse of 100, which is r, and if I take that 100, multiply it by the sine of this angle, I'm going to get this length, and I'm going to say that this length is equal to this arc length, which is equal to r. So I have r is equal to, did I do that right? I don't think so. No, yeah, I did it right. Yeah, so right here, if I choose this angle of 1 radian, if my angle is 1 radian, I have r sine theta gamma is equal to r. But we have one extra term we need to put in here. We need to put in the angle right here, because let's say I half this angle. Now my angle is only 0.5 radians, and my arc length is just half the radius. So keep that in mind. It's going to be r divided by 2. And what we're going to say is that this 0.5 is this value right here. So those are the same. This 0.5 and this 1/2 are the same. So if I just take this angle of 0.5 radians and multiply it by the radius, I get that arc length. And actually, that isn't even an approximation. Because if I'm saying that if I cut this radius string and then drape it around the circle to get to there, and I'm calling that 1 radian, then 1 radian times the radius is the arc length. You know, so that is so radians, this angle, times the radius is arc length. But what we're going to say is that, hey, look at this portion of the right triangle. I'm going to want to know that. I really want to know just this portion of the right triangle. Well, I'm going to say, it's pretty similar to this. It's just going to be gamma r. And even though the arc length is over here and it's definitely bigger, I'm going to say that is right there. Even though that this should be sine gamma times r, or r sine gamma. And that would be this actual length. This length right here is the hypotenuse, r sine gamma. So now let's, I think all we have to do is just half that, and we should be able to see, because at 30 degrees, or a half a radian, is close enough where this approximation is close enough. Okay, so here's the radius. Here is, if I took this radius and draped it up to here, I'd probably get to about there. There's going to be my 60 degrees. I'm going to half it, and I'm going to get to there. So this arc length, and then this is 0.5 radians. That is the angle. So that's 100%, 0.5 radians. This arc length is 0.5 times r, which is just r divided by 2, or 0.5 r. Okay, now look at this. This portion of the right triangle, I'm going to drop it down and then make a right triangle. Look at this. Like, this line right here is very similar to this curve. And as we get this angle to get closer and closer, this curve is more looks like a straight line. And we already said that this is 1 radian, this is a half, a tenth of a radian I can't even really draw, and that's 0.1 radians. 0.01 would be a tenth of that, and I can't even see it. And then so, hell yeah, that right triangle portion, the radius, the hypotenuse, right there, times the sine of the angle, can just be denoted as the arc length. And so that's where we get 0.004 radians. So that would be our angle that we're dealing with. So that's the angle. I'm going to take the sine component of it, which is that vertical component, multiply it by the radius, which is my hypotenuse, and that is going to be the vertical component. Cool. And when I do that, I'm just going to say it's equivalent to just the arc length, which we have defined as radians, so that's gamma, times the radius, so it's just 0.004 times the radius. And so right here we have r sine 0.004 is equal to 0.004 times r. So this right here, sine of 0.004, is just 0.004 by small angle approximation. There's going to be some discrepancy, but not mathematically enough. You know what I mean? The actual arc length is going to be 0.004. The sine of 0.004 is going to be, maybe it's 0.3999, and there's like 4 nines. But mathematically, it's going to be basically equivalent to 0.004. So keep that in mind anytime that you work with like approximations. Just actually throw them into your calculator and be astonished of how little difference there is. And when you're actually going to get at least 1% error. Because you can go up to 60 degrees and you're still just going to get 15% error. Like this is 8 or like 13% error. This is 85.6, you know what I mean, or whatever. Sine of 60 is 0.866. That's 86.6%. And the error on that's going to be like 13%. All right, and that's a huge angle. That's 60 degrees. And 30 degrees is going to be pretty darn close. You know, I always consider 30 degrees and under, but I can take the small approximation up to 60, and I do so for just guesstimating. And that's a worldly skill, especially for, you know, just kind of guesstimating things. All right, hell yeah. So back to, so now what this shows is that I can just have this chunk of steel be 1,000 by 1,000 meters. So it's 1 meter by 1 meter, 1,000 millimeters by 1,000 millimeters. This angle is going to be 0.004. this vertical stretch should be this radius. And I'm going to say that this length right here is equal to my hypotenuse. Because this angle are the same, because this angle is very small, that this hypotenuse is the same as the adjacent side. So this is 1,000. When we lengthen this thing or move it up into this angle, this is still 1,000. And both those are. And then so we have, but this component, even though we have small angles, just note that the sine component can actually be fairly tangible. Even though if this angle is always small, this is always going to be very close to the hypotenuse. But this, you know what I mean? This can grow appreciably. So hell yeah. So this component right here, if I just say this is 4 millimeters, so if I take this, where this is 1,000 and this is 4, then I'm going to use my equation that says this angle, where I'm going to say radians times radius is arc length. Even though this isn't an arc length, you know what I mean, and a swept up arc is going to look something like that, I'm still going to say that this vertical component up 4 millimeters would be the same as of taking this length, pivoting it right here, and then sweeping it up a height of 4 millimeters. So that's kind of what we're showing. And when we do that, we sweep out this angle that should follow this formula 100%, because we said this 10,000 is the radius. If we swept it up where this arc length was 1,000, sorry, this is 1,000, and if we swept an arc that was 1,000 long, that would be 1 radian. If we sweep it 500, that would be a half a radian, and so forth. If we sweep it 100, that's going to be a tenth of a radian. We sweep it 10, that's going to be 100th of a radian. And we're going to sweep it half of that to get 0.005, you know, so we're going to just do it 0.004. We're just going to sweep it up 4. So it's just good to go through that process, and that really helps you understand the small angle approximation. Instead of just hand waving, oh, I'm dealing with a small angle, hypotenuse times sine of the angle just becomes hypotenuse the angle. But that's what this is. This is the hypotenuse. This is the angle. So radians, and I like to say it in reverse. Even though you would be like r sine gamma is equal to that, that vertical component of that right triangle, and that's going to be very similar. That's going to be approximate the arc length. I'm still going to say, and that's just r gamma. Cool, because this sine gamma is just gamma. I'm still going to take this r gamma. Well, I don't know. I'm going to know that this is the hypotenuse and this is the angle. That's useful. But I like to say the phrase radians, which is this, times radius is the arc length. Because radians are bizarre. And radians times radius gives you something normal, and that's the arc length. Just as in radians per second times radius gives you tangential velocity, and same with angular acceleration. That's radians per second times radius is tangential acceleration. So radians, this value right here times radius gives you that something normal, which is arc length. And I swear, like unless you're taking like traffic engineering where you're doing circles all the time, I think people, like I graduated with kind of forgetting this equation, just that, like, what's the arc length of a circle? And that's kind of bizarre. And then just know that the arc length of a circle is still just a proportion of the entire circle. So if I have this to be 1,000, like what would be the circumference? Wouldn't the circumference be like 3,000? You know what I mean? Wouldn't it be 3,140? 41.5? You know what I mean? 3.145? Hell yeah. And then, so what do we have? Well, we have 4 millimeters divided by 3,000, basically 4 divided by 3,000. And what do we get? Let's say it was 4 divided by 4,000. That's 1 divided by 1,000, and we're going to get 0.001. And we have 4... Am I doing this right? Hell no, I'm not doing this right. This always trips me up. It trips me up because all of physics works with radius, but then all of kindergarten through 8th grade works with diameter. You know what I mean? So I get that equation mixed up all the time. Is that if I have the diameter, I'm multiplying by 3. And this is shame on me. And I think shame on all physics teachers that if you have the radius, you're going to multiply by 6. R times 6 is the circumference. And no one says that. Like, this doesn't even look like it makes sense. But diameter times 3, hell yeah. Diameter times 3 is basically the circumference. So same thing, radius times 6 is the circumference. So I'm using this opportunity to be like, hell yeah, I definitely need to drill that approximation into my head. Because like right here, I messed up. If this is 1,000, then my circumference is about 6,000. 6,000. And it's actually 6.28. It's the radius times 6.28. So that 0.28 is going to be 6,280. So that's what I have. Instead of 3,140, I have 6,280. Hell yeah. And so then I have 4 divided by 6,280. And again, same approximation. If I have 4 divided by 4,000, that's 1 divided by 1,000. That's 0.001. Am I even doing that right? 0.001. Hell yeah. But it's why isn't that not coming out? All I'm trying to get at is that, or maybe I'm not trying to get anything. Well, what the hell am I even doing? I'm trying to relate. Oh yeah. Then I have to like divide by a multiple of 6 anyway. So yeah, shame on me for even doing this. But yeah, no, this is good to go over the circles because I swear it's just like sometimes the most basic properties of a circle you kind of forget. All right, so oh, and I kind of lost this anyway, so we're just gonna booyah, start over. Hell yeah. But yes, so if this is my square chunk of steel and it's 1,000 by 1,000, and I'm going to make it into a diamond shape that goes up 4 millimeters, I can think of this as a radius. I could sweep out a circle. I already did that, but there you go. This is the circle. And then, so this circumference would be about 6,000. This would be 4. And that's just the proportion. 4 divided by 6,000 is just the like percentage of a circle. So this would just be the percentage of a circle. But when we're talking angle, like we still have to talk in degrees or radians. So this is so even though 4 divided by 6,000 is the proportion of the full circle. I just want to know what, and a full circle has six radians in it. So if this is just think of it as the proportion, and if any proportions, I like to multiply by 100%. And I think it's way easier to be like, oh yeah, this is the percentage. You know what I mean? So even though this is a proportion, this 4 millimeters up is a proportion of the full circle. I like to use the word percent. I just mentally can be like, oh yeah, if I move this up 4 millimeters, that's a percent of this full circle. Cool. Then I know a full circle is composed of 6 radians. Cool. Now I can do this. The 6's cancel. 4 divided by 1,000 is that 0.004. Why the hell was that so hard? I'm glad it was hard, because circles and radians, I don't know, just aren't your friend, and no one really teaches them in a way that's just like keeps drilling in just the basics of radians and the basics of dealing with the radius of a circle, and how 6 times the radius is approximately the circumference. No one says that. This 6r is equal to c. I've never seen that ever, and I think that deserves its own little miniature video. So maybe I'll do a 1 minute just to like throw this in to your wheelhouse. All right, booyah. Okay, so now we're understanding that if I have a 1 meter by 1 meter chunk of steel, and I reef on one end this way, reef on the other end this way, and form this angle to have 4 millimeters, I have maxed out the steel. And I know that this angle now is 0.004 radians, which is just this divided by that. And so if I have 4 divided by 1,000, this is another one. This should scream like, well, isn't that tangent? Well, not really, because 4 divided by this 1,000, I'm calling this to be the hypotenuse, but we're saying that the hypotenuse and this adjacent are the same. And in a right triangle, if I have the opposite divided by adjacent, that's what I'm comparing. This, typically, I would have this tangent right here. If I did tangent of this divided by that, well, what the hell does that give me? Yeah, the tangent of this length divided by that length, that gives me this. Cool. And tangent is just sine. Sine of 0.004 is equal to this. And, tangent is just sine of that divided by cosine of 0.004. Cosine of a small number is just 1, and sine of a small number is where you get that small angle approximation that you can just get rid of the sine, and then we just have 0.004. So hell yeah. All right, booyah. So there you go. So that is all the material can take. If I have steel and I have a small little square of it, I envision this square to be 1 meter by 1 meter, and I envision that I can only make an angle or a diamond shape where this goes up 4, and this length is 10,000, this flat length. And that angle that forms is 0.004. And that is all that can happen. If I go past that, people die, or my tool gets bent, and you know what I mean? And I want to design or only reef on something to where when I do torque it or reef on it, sorry, this goes this way, that when I let go of that torque or force or tension or moment, that everything goes back to the same, you know, every molecule goes back to the same location. That's kind of the magic of material mechanics. All right, hell yeah. And so, so that was the, I guess, you know what I mean? I think this is good. I'm just kind of going over in general terms the proof from the other day that if I have this bar, this is the little section right here. This section gets dropped down right there. I'm still envisioning that this is hollow. I think that's very useful. And back to our big, you know, chunk. And then I'm envisioning 2 rows of discs. You know what I mean? So these are forming discs, and we have a little square. And then as we torque this, as this side goes this way, and that side goes this way, this side goes up, that side goes down, and we get that diamond shape to occur. And we can only get that diamond shape to where these two, the diagonals, they get farther away, can only get, if it's still 0.2% farther away. But we don't have to worry about that anymore because we've just shown that, hey, if that diamond shape gets to be like this, where this angle becomes 0.004 radians, that's our max. So that's the whole idea behind shear. is that we're not trying to do the math every time to figure out, hey, like what's geometry is happening, like how is this diamond shape getting longer that way and crunched in this way. We're just saying we've already done that proof, and we're getting this angle to form. And if we do get this angle to form, that's the max. And then also, this angle forms at every 4 molecules. So that's kind of interesting, because if I have a steel bar that is just made of 2 rows of molecules, so this row goes on and on and on, and this row goes on and on and on. So that's what my steel bar is made out of. And then I want to tweak each of these molecules. So like, the first 4 do that. So that's what happens to these first 4, and we get this diamond shape. Okay, hell yeah. So this is where we're welding it to the wall. Okay, so that location does not move. But these 2, I can get to move. And so I get this diamond shape, and let's say I don't do anything to the other 2. But now, hey, I want to move these next 2, and I can move those next 2 down. And then let's say I don't do anything to the rest of them. This did get lower, but now let's say I want to move these 2. So I'm going to, just kind of apply a force on those, and then push those down. And I can keep this angle. This is the max angle. The second I get those 2 molecules to go farther apart, you know what I mean? We killed people. But then the next 2, if I didn't do anything to the rest of the beam, it would just be straight across. But then I'm going to move the next 2 down. And you can see that this beam, I can apply that downward force on each of those slices. I'm going to call these vertical slices of molecules, to where this angle forms throughout the entire bar. And guess what that angle is? 0.004 for steel. It's going to be a different number for different materials, but in material mechanics, this number is pretty small. Just like if I have a bar that's 1,000 millimeters, I can only lengthen it 2 millimeters. That's hardly noticeable before I've permanently stretched out a bar. Same thing with compression. It's very difficult to maybe see those lengthenings or compressions unless the initial sample has a really long length. Like even the Golden Gate Bridge, you can look at it on a cold day and mark a location of where a piece of metal was, like of a big section. If you know a big section of a bridge is totally rigid and it's made up of multiple sections, and those sections like are on rollers, and then one end is fixed, it would be kind of a cool thing to, especially on my drive, if I was driving to my brother's house in Bozeman, like maybe go to one of these old bridges and then just put down a little piece. If it's a hot day, put down, like just say, hey, just take a little marker and a little piece of tape or something, and then mark where that bridge is, especially if it has a fixed pin and then some sort of roller. And then on a hot day, it's there. And then on a cold day, it's there. And because if I have a meter of bridge, I could get a difference of 2 millimeters. But guess what if I have a 10 meters of bridge? That's 20 millimeters. It's almost an inch. And so on and so forth. You know what I mean? So, hell yeah, 10-meter span. If I got a 30-foot span, I might be able to mark out a whole inch. But that's not true, because thermal hot to cold is not going to take a bridge lengthwise from 0 to max. 0 to this 0.2% is the max a material can take. What temperature would do, so it's always good to understand like the power of like what is temperature going to do. Well, I a tenth of that, even 100th of that. So if I have, I still might only, if I have a 10-meter stretch of bridge, I still might only be able to tape out and notice a 2-millimeter change due to the temperature. So, but those are good parameters to have. Every proof or property of material mechanics, I always want to take a simple, something that I can be like, hell yeah, I got a meter by meter, especially for shear. You know what I mean? If I have a meter by meter plate of steel, I can reef on one end, reef on the other, and I can do that 4 millimeters. Even though, like, this is a bad example, I need to get a better one for shear, because I wouldn't be able to do that. You know, where I could actually take a bolt and a long bolt and then put it in a chunk of steel and then tighten it where the bolt lengthens, and I could lengthen, like I could measure a meter long, because you can buy, you know, almost a meter long threaded rod, and then I could you know, get a bunch of steel and then lengthen that rod. But that's the thing with calipers, I wouldn't be able to measure that, but maybe, and then lengthen it. Try to feel like I stretched it by 3 millimeters, and then measure it before and after and see if it's permanently deformed by 1 millimeter, because we know that I can stretch it 2 and then let go and everything goes back to the original location. Stretch it 3, I'm going to have 1 millimeter of deformation. And just know that steel, you can take this 1 meter bar and potentially get up to a 30% increase. You know what I mean? So that's 300 millimeters. So our game is just take 1,000 millimeters of bar and lengthen it 2 millimeters. You know what I mean? But just know that plastically, you can at least do 5% even with a bolt. So if I have let's do this. If I have a 4-inch bolt, that's pretty common. That's 100 millimeters. And what's 5% of that? Well, 10% is 10 millimeters. 5% is 5 millimeters. So hell yeah. So in 5 millimeters, that is, let's say it's almost 1/4 of an inch. You know what I mean? It's a little less. 25 millimeters is 1 inch. So, yeah. So it's about 1/4 of an inch, just a little bit less. But that's noticeable. I can tighten this thing in a 4-inch block of steel, and then measure where this bolt face is, and then as I'm tightening it, lengthening that bolt. And honestly, I should do that just right after I make this video, because that would just make sense. You know, the more practical applications you can have, and I really should start making physics examples that I can be like, hey, this device shows this property, because I don't even have to ruin the bolt. I can take that bolt and then lengthen it. No, this would destroy the bolt, but I could take this bolt and lengthen it 1/4 inch before it actually, I could lengthen it 5 millimeters, and guess what? Is it going to go back to 2 millimeters? Hell no, because now we're just have a length of 100. It's going to go, if I stretch it 5, it's going to go, it's only going to go back 0.2, you know what I mean? So it's going to go back to 4.8, you know what I mean? So, hell yeah. But it's really good to have that, and this is just the basics. But look at this. This proof is just taking the basics. It's just working with shear, which sucks because it doesn't get taught very well. And just know that all shear is this diagonal deform, which is just lengthening of the diagonal and crunching of the opposite diagonal. And still, things like molecules can only lengthen and can only compress so much. Those values can be different for different materials, but for steel, what it can lengthen is the same amount that it can compress. So that's kind of cool. All right, hell yeah, get some water. All right, so this example shows that the longer, this was a good example, because the longer the steel bar, the more downward deflection. See this? If this was a meter long, I would just have 4 millimeters to build up right here. But let's add another 0. Okay, so now this is 40. You know what I mean? It's almost a couple inches. And then put another 0. You know what I mean? Hey, let's say this is this many millimeters. That's 1,000 meters. That's 100 meters. If this was a 100 meters long bridge, and then I took every molecule, I could move this down 4 times 4, 16 inches. So there you go. So, and the wild thing is, if I have a 100 meter long bar of steel or bridge of steel, and then I push down, just continuously in this, creating pure shear of those layers, I can move this point down to 16 inches below its original location and then let go. And this would make sense if it was sideways, just so it's not under its own weight. Like I'm applying forces very particularly. And a problem, and then getting pure shear to happen, you almost need like devices like fins welded to this on like rollers, that the rollers move in tracks, just so this length doesn't change at all, and that each little location can slide, almost like if this is a slinky, each ring of the slinky can slide past each other. But if you do that, I can move this whole beam down to 16 inches if it's 100 meters across. Which, I don't know, does that sound like a lot? That doesn't sound like a lot to me. But we're going to see how that compares to this. Because, oh, no, it does. That is wild. Because, I think this will be pretty cool. Because this beam, all it was just 2 rows of molecules. And let's say its thickness was just 1 molecule. So there you go. So we have... And I think this is very useful when thinking about material mechanics, because material mechanics, they always throw like a tiny little square on here, and you're supposed to rack your brain of what that actually means. Like it can be either an infinitesimally small little location or just a small enough location. I forget what would be the difference. But hell yeah, when you can make something that is fundamentally made out of atoms that can still obey the properties that you're trying to get out of material mechanics, I think you have come across something. So we're just so all these atoms are in the little rows, and with this, we said that we had 100 meters of them, and we can drop this down by 400 millimeters, which is 16 inches. So we have... I'm just going to mix. So we have 100 meters, and we can drop this down 16 inches, which is appreciable. Now, it doesn't seem actually. To me, it still doesn't seem like this is a big deal. But when we get into torsion, let's see if I can explain why that is. Because when I have this, I'm just going to say now that we're going to get something on. I'm going to say this is a 1/4 inch. This is a 1/4 inch diameter, made out of steel. And it's 1,000 millimeters long. And I don't know, just for me, it's useful to mix units. Just because if I said this was 20 millimeters, actually, what the hell is even a 1/4 inch? We said that was about 5 millimeters, 8 millimeters. I don't know. That doesn't help me. But 1/4 inch, hell yeah, I know what a 1/4 inch is. And then, so if this is 1/4 inch diameter, what's the circumference? The circumference is times 3. So it's 3/4. So the circumference is 3/4. So this is where I like to combine American units and then go back. I don't know. Just for me, it's just really easy for me to visualize a 1/4 inch bar. Maybe it's very useful to you to visualize an 8 millimeter diameter bar. Just know that 24.5 is very close to 24. And 24 is a multiple of 4, and it's a multiple of 8. So 24 can be divided by 4 to get 6. 6 times 4. And is that right? So 24.5. Did I mess that up? So 1/4 of an inch is 6 millimeters, and I was guessing it was 8. So I was wrong on that. Hell yeah. So because 6 times 4 is 24. So hell yeah. So if this was 6 millimeters in diameter, then the circumference would be times 3. So it would be 18 millimeters. And 18 millimeters, I don't know, 18 and 24 seems like 3/4. So we have 3/4 of an inch in circumference. So let's do this one. Because what we're saying is that if this is 1,000 millimeters, and we're not going to make it, we're just going to do 1,000 millimeters, 1 meter. I could go buy this 1/4 inch steel bar of 1,000 millimeters. I can weld it to this end, and I should be doing this experiment, and I should have this experiment at the ready. even just have like a flat plate on the ground. I'm just thinking of like what would be the best way to show this experiment. Weld a flat plate to a 1/4 inch by 1 meter steel. You would call this a, what the hell? What do you call a steel? I don't know. If it's square, you call it a, I'm bummed. Anyway, I don't know my steel yard terms. But anyway, so you get that and you weld it here, and then I would just weld a handle on it. And then the whole idea is how much angle can I get? How much angle can I make? And then let go and have this go back to the same, and then I could draw a line on it. So I'm not tweaking the line. You know what I mean? So then I could make this vertical and stand on here, and then twist it. And this one, I thought I did this before. I thought I just did this in the last video, and I was surprised that I could move it a fifth. I thought I could move it about a fifth of a rotation. So that's almost a fourth. So I could almost do 90 degrees. But I could do about 60 degrees, let's say. Now is that gonna be right? And that's what we're gonna find out. How do we find that out? This is good because it's kind of just like mini problems. Is if I have this bar that's 1,000 mil, this would be like probably the ending part of this video. If I can solve this, hell yeah, because we're just kind of going over the introduction of what we did yesterday. I really want to get into shear, but I guess that's just not for this video. But we're just kind of relating this imaginary bar that we made that was 2 atom layers thick, and the fact that shear, we can actually get it to drop down. You know what I mean? Not that impressive, because this angle still, if it's steel, is just still 0.004. You know what I mean? And if we said that this was 1,000, like 1 meter, I can only drop this down by 4 millimeters. Now here it is. So 4 millimeters, when we look at this, doesn't seem like very much when we just drop this thing down. But guess what? Like on a cylinder, is this going to even work? I think so. And maybe we actually have to go back to the derivation because I'm probably messing up one thing. Yep, and we should actually kind of go back to this this derivation, because this derivation has 2 angles that go on. With this, we have our bar, and we draw this straight line on it. And this is just good for me to like kind of take a moment. And when I torque it this direction, that this line makes a diagonal. And I'm just going to say this diagonal is kind of a small angle. So it just kind of looks, it doesn't look helical. It just kind of looks like a small angle. So now what we have is we're actually going to take a section of this. So if I can measure that angle, so we have a small angle, and we can get a number on it right there. Now, now the angle that we're measuring is this angle from the radius. So I'm going to say, hey, this is a slice of a circle. It used to be here on this line, and now it's here. Now I'm going to go to the middle point, and then I'm going to say, hey, this slice used to be here, and now it's here. And now I'm going to go to the end point, and I'm going to say, hey, this slice used to be here. Oh, look, it's in the same location. Because even that part right here of this proof is a little bit tricky to be like, oh, okay, so this angle forms over here. It's half. The angle is half right there, and it's 0 over here. And we have a linear change in that angle. Okay, that angle is irrelevant. Oh, no, that's where it's like that is where like kind of the calculus comes in. So if we take a look at our big cylinder, and I'm going to put the 2 slices right over here. So here is 1 row of atoms, and then the very second row of atoms. And I'm going to say this first row of atoms is nicely welded to this wall, and we're tweaking it this way. This second row of atoms is the ones that we're tweaking downwards. And so we get that it used to be a nice square box, but now this box is angled. And so that's the shear that we're picking up. And we've just talked in thoroughly that this angle can only be 0.004. That is the max angle that we can have. Okay. And then what we have is the fact that this first, so if we look at the inside of this first disk, I'm going to say its center for this disk is right there. This angle, like after torquing, this atom did not move. But if I go to the second disk, part of this disk, this atom used to be right here. This was its original location, and I'm going to say this was the line up to it. Now this is where it is. And so this is the smallest little distance that we can have, and I'm going to call that dx. And this angle that forms right here is d phi. Hell yeah. And every next disk is also going to rotate a d phi. And those are going to all add up for this final rotation of phi. And this is just phi at length L, so all the way out to the end. So this is phi. This term right here should actually be phi evaluated at L, where this angle varies along x. So this is phi at L, and this is phi at any point x. And then just know if we take a tiny differential slice, and sometimes, like I'm taking the differential slice right at the very beginning, and the smallest incremental change that we're going to have is d phi. And so what they do is they take that slice, sorry about that. Oh, wrong way. My bad. Get back. All right. All right, so they're going to take that slice at some location arbitrary at x. And I think that is the first place where this derivation gets a little confusing, because if I draw this straight line on here, and after I torque it, that straight line is going to become a helical. And then once I take this little segment, we're going to compare this straight line right there. I mean, this angled line is this angled line right here. And then this straight line right here is not this original straight line. So when we take this straight line that used to be straight, tweak it down, we're going to assume that it should be straight, but it's not. It has this angle, and then this is the differential angle to form d phi. So like we showed that the first one was welded, the second one shifted down. Well, it doesn't matter if you take that slice right here. If you take that slice right here, and these are the two layers, this one appears fixed, and then this one shifts down, and then we get that shear to happen. And the max angle that we can have is this angle. So that's what we get. And what we're going to find is that on the surface of this, that's where those molecules are going to have that max angle. If because this angle right here, this is d phi. This is our small differential length. This is the angle that gets formed. And this is the shear max. So this is the number that we know. So now we kind of work backwards. We know that the material property of steel can have this max angle, this max diagonal angle of 0.004. So if that's the case, I know what this angle is, and then so I know what this arc length is. This arc length is the angle times the radius. It doesn't matter, and then they're saying this is a small angle, so it doesn't matter if you take the hypotenuse or the adjacent. And so we're basically going to take the adjacent. The adjacent is dx, so let's go through this. So we have this max times dx, radians times radius, is this arc length. But now we also have this to form. This is another angle. We have a radius. So this angle, d phi, radians in d phi times the arc length r, these two are equal. So now what we can do is we can get an equation for y max and say that's just dx downstairs. And so that is going to be the change in the angle with respect to x. And I guess that is where you would, oh, don't quote me on this, but I just know it's linear. So we're going to say the total change in angle from the fixed end to the other end is going to be phi, because that's phi at L, which is just phi. And then dx is just L. That's going to be the change. And so we have this is and they call this the rate of twist. And I think the second they actually start calling it something, I swear my brain loses brain cells. But we're going to have phi divided by L times r is this y max. But then what were we saying? It's just like, well, I already know what y max can be for the material. So maybe I can solve for something. So I can say, yeah, this is phi divided by L, and then we have times r. So this equation is phi divided by L times r. I know what L is. I know what r is. I know what y max is. So hell yeah, maybe I do actually want to solve for this. And that's what we're going to do and be done with this video. So hell yeah. So that max angle over here, and I think, you weld this bar over here, and then you do that experiment where you twist it in this direction, and then you draw a line on it, and how much does that line change? Does it change, 1 radian, 60 degrees? We're going to find out. So rearranging this equation for this, we're going to keep this over here. L goes upstairs, R goes downstairs. So we have Y max, L goes upstairs, R goes downstairs, and this should give me the angle. And does that make sense? This is in radians, this is in length, this is in length, and we get radians. So we're going to have 0.004. Length is 1,000. So that's just 4. So we get 4 up top. The radius, we're going to have 4 divided by, and then the radius is also something that's pretty similar. We said this was quarter inch diameter. And if it's quarter inch diameter, that's 25 divided by 4, or 24 divided by 4, which is 6. So 6 millimeters is our diameter. Our radius is 3 millimeters. Hopefully I didn't mess up anything. And we've got these two terms are 1,000 times 0.004. So that's 4. So we get 4 divided by 3. And that is our angle in radians. So we can do 4/3 a radian. 1 radian is 60 degrees. A half a radian is 30. So 45 degrees. So this is such a cool experiment. And I'm going to go, what the hell time is it? It's probably too late to go rummaging through my storage unit. But maybe we will. Maybe we won't. But anyway. I really should set this experiment. Weld a plate of steel on the ground, 1 meter, quarter inch. Make a little handlebar that I can twist it. And guess what? I can twist it 90 degrees because these molecules on the surface are getting maxed out. And the cool thing about this experiment, it doesn't matter if it's hollow or not hollow. And I should do it both ways. I should buy 2 equivalent, a hollow tube and a non-hollow tube made of steel, set up this experiment, and what you would notice is you can only move this thing 90 degrees before these molecules on the surface, and again, that's the take-home point, that diagonal gets so much where these get permanently deformed, and these crunch in where they get permanently deformed, And you can think of both of those as just maybe filling in voids and then kind of supporting themselves in that new location. You know what I mean? Whether it's compression or in tension, steel is always trying to fill in the voids and then kind of hold itself in those new orientations, because you have iron atoms in a sea of electrons. For the most part, it is, I'm just going to say electrostatic forces. It's weird. I need to also double prove why it's linear. And I just from my perspective, it's just because it doesn't move very far. Like a spring, if you move a spring that's this long and you move it from there and then you get a reading, you know what I mean, to this location, and that's what your reading is, and then you're just going to move it a fraction of a little bit. Well, no, you got to do this 3 times. So I'm going to move it to here, get this reading. This spring was right there. I'm going to move it to there, get that reading. I'm going to move it the same distance, and it should double the reading. You know what I mean? So that is the linear relationship. Even though I got twice far, I moved a distance this way. Hey, maybe this force is the inverse square. But look at that. That number and that number, the inverse square, is very linear. So we talked about that in the other video. But I do need to review that, because I think that is a very crucial element. That's a great place to ask why. Why in material mechanics does every bond, whether it's covalent or any chemical bond, if you just move things just a tiny bit, it's going to move in a linear, elastic way? That is very fascinating. All right, hell yeah. So whether it's hollow or solid, if it's 1/4 inch, and then I torque it, I can only torque it about 45 degrees. I was going to about say 90, but 45 degrees. And that's noticeable. And then at that, and this is a really good experiment to use your feel sense, because you can tell when you're bending something. Like, and I can tell, especially when I've done these, you know, like actually done the beam equations and then stepped on a beam and I'm like, holy Toledo. Like, this was supposed to hold me and it barely holds me. And you can kind of tell that. You're like, the equation just says it's going to hold me, where if I go back, it's going to go back to the original shape. So this is one of those where if I go to 45 and let go, this straight line is going to go back to straight, you know, after it rolls down 45 degrees. And it doesn't matter if it's hollow or solid. Both those are going to happen. Now, the elephant in the room is like, well, isn't it going to take more force to tweak the solid one than the hollow one? And hell yes. Always the solid cylinder is going to be stronger than the hollow. But for whatever reason, physics books and this material mechanics books, they show like, a hollow sphere is stronger. Well, not necessarily stronger if it's the same diameter. But if you increase this diameter just a little bit, it could be stronger, and you have used less material. And what that gets into is, well, let's just leave it at that. But why is this one filled with material stronger? Well, you have to move more molecules. Like on the surface of this, I'm just shearing those surface molecules. And so that really gets into the next section, is if this bar is literally just a hollow sphere of 1 molecule thickness iron atoms. In torsion, it's not going to be very strong. I mean, that would be a fascinating one to do, and I think that is very useful to be like, how big is an iron atom? And if this 1/4 inch, how many iron atoms are going to fit in a circle? This is very chemistry-esque, because you're going to get a number. Like, is it going to be less than a mole? It's going to be less than 10 to the 23, because 10 to the 23 of anything is either 1 gram of hydrogen, or for iron, what is it, like 90? I don't know. It might be up to 90 grams for an iron. I have no idea the atomic mass of iron. 70 to 90? I have no idea. But anyway, so I would have 90 grams of iron molecules. But I can thoroughly say that if I took a steel bar and sliced just 1 layer of iron molecules, I would for sure not have 90 grams. I would not have 1 gram. I don't even know if I would have 10 to the negative 7. If I had to guess, I would probably have 10 to the negative 16 to 17. I would say negative 14 to 18. It's always good to guess, you know what I mean? and then do those. Those are very good physics questions. And you can just do it by density. You know what I mean? You can be like, hey, how much, if I have 1 inch of steel, how much does it weigh? Get a number on that. How much does 1 mole of steel weigh? Get a number on that. How many, you know what I mean? And if this number, let's say this number is equal. Let's say in 1 inch of steel, it weighs this many grams, and a mole of steel is this many grams. There's a chance it's pretty close. Well, then I know in an inch of steel, I got 10 to the 26. I have no idea. 23? 6 times 10 to the 23. And even this, 6 times 10 to the 23, you should think a mole is actually 10 to the 24. You know what I mean? Like that is a more useful number to have in your head than this 6.022 times 10 to the, is it 23? I have no idea. But yeah, 10 to the 24. And 10 to the 24 is a cool number because that's also the weight of the Earth in kilograms. You know what I mean? So hell yeah, there is a mole of kilograms in the Earth. All right, booyah. Oh man, I am needing to use the bathroom. Sorry if I'm making any noises, but I think we're done. So yes, you use physics. Like these are great examples of like, hey, how many? But yeah. So yeah, there you go. So if I had 1 iron atom and 1 iron atom, and I pulled them apart, how much force can I put on there? That's a physics problem. It's going to be a small number, but it's going to be a number. Because if I have 1 inch of steel, then I know how many, iron atoms I have. And then this is a cube. And then so I could take the cubed root of that. See, we're making noises. I apologize. So take the cube root of this, which if it's 10 to the 24, you know what I mean? What would we do? Don't you just divide this by 3? And hell yeah. And I'm sweating. And so you have 8. You know what I mean? So you're going to have 10 to the 8 along this line. And then so if I took a slice of this 1 inch, then I would have 10 to the 16. And then I would have 10 to the 16 of those. And 10 to the 16 iron atoms can actually hold 50,000 pounds or 58,000. So there you go. So now we actually have a number on them. And if I just had, and so that's 10 to the, that's 2 slices of 10 to the 16. You got 10 to the 16 iron atoms there and 10 to the 16 iron atoms there. And that's, those bonds, all those, create 50,000 pounds. So if I just said, hey, what's one of those? I'm going to take, and then this, let's hell around to 10 to the 1, 2. This would be 10,000. So 1, 2, 3, 4, 5. This is 10 to the 5. And I'm going to divide by 10 to the 16. And then I'm going to do 5 minus 16. And then this is how I've been doing subtraction now. So if I have 5 minus 16, I know I'm going to get a negative number. That's the first thing I'm going to do. But now I hate subtracting. So now what I'm going to do is I'm just going to pretend these are on a number line. 5 and 16. And I can move either number. Typically, I'm going to increase because that's adding is easier. So I'm going to move this number up to 10. This one goes up to 21. 21 minus 10 is 11. So I'm going to get negative 11, which even looking at this, I could have got there, negative 16. Anyway, but yeah, that's kind of a double check on your subtraction. But we have 10 to the negative 11. This is pound. That's pounds. So there you go. So 2 of these can take 10 to the negative 11 pounds. And then there you go. So, shear is so sucky, but still, if I have these 4 boxes right here, and I move one up and I move one down, I am still moving. See, and this is for the next video, because that's what we're going to get into, is how if I have these 4 iron atoms, I just found that if I had 2 iron atoms, you know what I mean? It's going to take 10 to the negative 11 pounds to pull them apart. Or that's the most force I can put on them before, it becomes deformed or breakage. So how about shear? You know what I mean? It is still, these two are getting farther apart. So I could just do that. I could just say, hey, I'm just going to really simplify this and be like, I'm going to put a force down this direction and a force down this direction. But you got a couple things going on, because I have to put equal forces this way and equal forces that way to even do that. And if I have these two forces, they're going to add. You know what I mean? They're going to become 1.4. You know, you can get a 1.4 there. And if I have 1.4, what are we even doing? But yeah. So, yeah, shear sucks, man, because it's not intuitive. So I'm going to go back to the drawing board and make that intuitive. But still, I think the take-home point is like, well, like, even though we get some square root 2 stuff going on, can't I just say, I'm just going to pretend that when I push down on this one and you know, do the whole shear thing, I'm just going to say I'm just pulling those apart. So I'm just going to say it's very equivalent to axial tension. Cool, let's do that. And then so, hey, if I have these 4, then I can only put a force of 10 to the negative 11. And then I think that is that is where, like, your mind will explode, where this seems like you got to do some free body diagrams. And for what reason? You know what I mean? Just to get an approximation that you might mess up the calculation anyway, where you can just be like, hell yeah, I kind of know it's just 2 that are getting pulled apart. Who cares about the other ones? And then, well, you know, and maybe this 1.14, I always thought it was, like, yeah, I always thought it was very, I have no idea. And then you get this idea that, like, if in shear, like, because right here we still have, like, this shear face, they're going to say, hey, how much area, surface area do we have right there? We still just have 2 molecules. So they're going to show that. If I have shear this 4, this sideways area is still just 2 molecules. And then so that's going to be the area. Yep, just like if I have 2 molecules being pulled axially, the area is just 1 of those. So if I had this 4 molecules, the area is 2. Hell yeah. But for whatever reason, for steel, there's just a factor of like a half. You know what I mean? Like shear is just, so like all this math, and at the end of the day, everyone just does an approximation anyway. So what I'm getting at for this is, if this hollow tube is just 1 layer of iron atoms, and then they're just, every slice is just another layer of iron atoms, at some point on there you're going to get 4 iron atoms in a square, and you can only put so many force on those. And so back to this diameter is 1/4, the circumference is 3 times that, that's 3/4. That's very similar to our inch, which we said had 10 to the 8. So I'm going to have 10 to the 8 in a row. I'm going to have 10 to the 8 iron molecules next to 10 to the 8 iron molecules, and I'm going to pull these this way, and I'm going to pull those that way. And if I just had 2, you know, little packets of 4, and I pull this one this way and this one this way, how much force can I do that with? Well, I would pretend that these weren't there and these weren't there, and I'm just pretending I'm pulling 2 axially. So even though I have up and down, you know, 2 layers of iron atoms, I'm just going to equivocate this as pulling 1 layer of iron. I think that is an okay approximation. Like, honestly, like right now I'm just like, I have to go back to the proofs of this. But with material mechanics, it's still good just to kind of guess like what you think would be going on. And I'm going to say, hell yeah, when we get this, we're just pulling 1-on-1. And then so how much force could we pull? Oh, that's interesting, because we're going back to that. If I do this experiment and weld this 1/4 inch bar. The question is, how much torque am I going to have to apply? If I do put a handlebar on this, how much force am I going to put that way, and how much force am I going to put that way? Like, what's the couple going to be needed to actually shear those? And so it again goes back just to having four, now we're doing it this way. And if I make those into a diagonal that are now this way, how much force is that going to take? And that's kind of, it's tripping me out. But, just from the realistic perspective, it can't be too much more or even too much less than just pulling. These four, to get these two to shear back and forth, I would just say, even if I think it can take twice as much, half to twice, that's a pretty decent guess. So hell yeah. And let's do this. So we took a 1 inch piece of steel, and we said we had 10 to the 8 by 10 to the 8. So now we know the two slices that we have, and those are the interactions. We're going to pull those apart, and so that's pulling things apart this way. Shear is pulling things past each other, where we kind of have this going on, and so when we pull things axially, it's going to be the number of these two things that we have. That's important. When we pull things this way, it is going to be it's still the number of these little boxes that we have. And we could even say that just one of these boxes of 4, it takes 4 boxes of material to, I think this is very good, because this is where the half comes in. If I have 4 of these, 4 in a box of material, I can say it's equivalent to just having 2 in a box and then pulling it axially. And I think that can be a very good mental equivalent of why, if I have some material and I'm shearing it, it's going to take half the force to shear through that than if I had that same material and I pulled axially. And so the deal on that is, if I have a bolt, let's make it not so phallic. There we go. So if I have still not getting, there we go. I have no idea. I'm trying stuff. Yep. Hard to draw anything. Okay, hell yeah. So if I have a bolt and I shear through it, meaning I put a load this way, that's the classic, you'll put a load diagram, with some arrows, and then a load that way, and it's going to rip through that. The other way I could do is just pull it apart this way. So what we find is, and the both are the same surface area, but what we find is, like, shearing it this way and that way requires half the force. This would be 1/2 F, and this would be 1F. And I'm just so glad, in real time, I keep patient and try to get a simpler explanation for things, because I think we just did that. And then we can kind of end on a high note. But yes, if I have a box of 4, I'm just going to equivocate it as a box of 2. So there you go. And so in this case, I have 10 to the 8, 10 to the 16, because it's 10 to the 8 times 10 to the 8. 10 to the 16 is equivalent to 50,000. Cool. And so I would have to say that I would have to have double that, which when we're talking 10 to the 16, double that is just 2 times 10 to the 16. Okay. So, but now let's talk about torque. And because when we torque this, torque is a moment. So we're applying a force this way and a force that way, let's say. Those are our forces. And then we have some sort of distance between here, or half distance, d divided by 2. And then we're applying a torque. So let's just make up a number. I think I need to have this 1 foot apart, and I think in the 1/4 inch bar, getting it to bend 1 meter, I think I would have to put 10 pounds, 20 pounds? Let's just say 20 pounds. Okay, and like I need to put 20 pounds on this and 20 pounds on that. Let's just say 10. So let's just 10, and then there's going to be a 1 foot difference. So I'm going to put 10 foot-pounds. And that would get it to bend. No doubt it would get it to bend. I just don't know if it would be right at the max. So I'd be between 5 and 40 foot-pounds. But 10 foot-pounds, pound-feet. So that's going to be pound-feet is going to be the moment generated. And that has to be resisted. Well, and that's why I always look at moments as forces. You know, anytime you see a moment, we'll just make it an equivalent force. And yeah, you're going to have them separated by a distance, but who cares? But they're still forces. And then the free body diagram says that these molecules have to resist the force. They do so by doing the shear. So we have, you know, that little square box of 4. And if this thing is getting tweaked that way, these molecules have to push back that way. Well, I mean, this shape's going to form on this. And so, and then this face, if we cut on that face, is going to go up. This is going to go down. We're going to get that diamond shape to form. But this is the force. We're going to call it a shear force. And that force is a distance away, which is the radius. And on the opposite side is going to be another square box. And that is also going to do the same thing, go down. And that distance is a radius. So if I take that shear force V times the diameter, that has to equal to my 10 foot-pounds. And so I have 10 pound-feet, or however you say that. And then my diameter is going to be and then let's get this in inches. So I'm going to have 120. So I'm going to have 120 pound inches. My diameter is going to be 0.25 inches. And then so that's going to be 1/4. I'm going to take this 1/4, multiply it to the other side. So my shear force that I attribute to all of these molecules in this ring has to be 120 times 4. 100 times 4 is 400, so it's going to be 480. Let's just say 500, and let's just round this up to 1,000. So I need 1,000 pounds of shear. So I need so those molecules have to resist 1,000 pounds of shear. And we said that if I had a 1 inch of them, I would have 10 to the 8. And how do we do this? If I had... Yeah. So in this is kind of fascinating. If I have... This is where we're going to take this example where we have a 1 inch square block, which is 10 to the 8 by 10 to the 8. Heck yeah, that's 50,000. Or that's 10 to the 5. 100,000. So that's 10 to the 5, and I have 10 to the 16. So I have 10 to the 16 atoms holding back 10 to the 5. And that's going to give me 10 to the negative 11 per each of those. But if I just have one strip of 10 to the 8, if I just have 1 inch, if I just have this, if I just have 1 inch of atoms and 1 inch of atoms, and that's my bar, it's very thin, and I'm pulling on it axially, then each of those is 10 to the negative 11, and I have 10 to the 8 of them. So how should we do this one? I'm going to get a negative. I'm going to go 8, 9, 10, 11. So still, I know, this is how I subtract numbers now. I have negative 11 and then 8. I know I'm taking the difference between them, which is just 8 minus 11. I can get it in that form. But still, I'm going to say 8 is on a number line and 11 is on a number line. I'm going to look at the overall number of this and say I'm going to get a negative. That's the first, just so I don't make a huge mistake. And then I'm going to say these are on a number line. If I move this up 2, then this moves to 13. Cool. And then 13 minus 10, the difference between is very easy, and so we get negative 3. So there you go. Because even if I just did this, 8, 9, 10, 11, I might mess up and do positive 3. But hell yeah. So we have 10 to the negative 3. I don't even know what value that would be. But what were we saying? We said if we had 10 to the 16, we get 10 to the 5. Or no, each of these atoms can hold this much force in pounds. And so we're going to have 10 to the 8 of them in a line. And so we can hold a force of 10 to the negative 3. Yeah, that's it. If I just have one row of atoms, I can only put a force of 10 to the negative 3. Oh, and I see where this problem is going to break down, because it would be physically impossible for me to find a hollow sphere that was one atom thick. And so, but yeah, if it's one atom thick, it's going to take 10 to the negative 3 pounds if I have 1 inch of this. And this cylinder, I'm just going to say, was 3/4 of an inch. I'm just going to say it was 1 inch. And so if I have 1 inch of these, it's going to take 10 to the negative 3. Now, how many rows, you know what I mean? If this is the outer row, that's going to be 1 inch. And then we have the next row, and then the next row. And the next row gets smaller. But guess what? This outer row can hold back at a radius of r. The next row can't hold back at a radius of r. So this gets into the next proof that we're going to do. And then so it's just fascinating. What I like to do is just find a sweet spot. I'm going to say 50% of the juice. So I'm going to say yeah, let's say, yeah, we have this. How many rows of that do we have? Yeah, because if this is only a 1/4 inch, oh, this is bumming me out. Sometimes a good way to do it is just get some sort of thickness in here. Like if this is a 1/4 inch, then that's the diameter, right? Is that what we're thinking? 1/4 inch diameter. And then so this is going to be 1/8 of an inch. I'm just going to go 1/10 of an inch. So there you go. So I'm going to say this thickness is 1/10 of an inch. And then here we had 10 to the 8 in an inch. And so if I just have 1/10 of an inch, I'm going to have 10 to the 7. So hell yeah. This is really bumming me out. But this is good to actually think of how strong one molecule of iron is next to another one. And then kind of approximate this from just a chemistry perspective. And see if we can do this. Hopefully I can get halfway accurate. Because, yeah, it's kind of hard to approximate that, like, hey, because as you know you have material in here, it can't resist a torque. So, yep. And the outer surface is the only one that can only get up to that 0.004. The inner surfaces don't have that 0.004, and therefore they're not holding back torque. You know what I mean? Like if you don't get this shear to happen on the inner surfaces as much, if the inner surfaces don't really have a shear, then they have some sort of distance that they're resisting a torque, but the shear that they're getting sheared isn't very much. So if I have some material and I just don't make it into a diamond shape that's not very diamond-like, it didn't take much force to do that. And so that's what we have as we go inside the cylinder. But it's still just a good approximation to be like, well, how much area is on the outside? And so what we did is we took is that pretty good? We took the diameter, halved it, turned it into fifths. That wasn't very good. Because if we took the diameter, which is 0.25, and then we had no, I thought we were doing pretty good. And then this was 0.25. This was 0.13. Which was, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0.13, 0 Oh, I guess that would have been the radius then. And then we're going to say all the material is right there. Oh yeah, so that's a horrible approximation because we're actually saying the bulk of this material is resisting the torque, but that's always good. It's always good to maybe like err on the high side. Well, this would be erring in the wrong direction, but let's go with it. So this distance right here is, and then we're going to take this donut of material and then stretch it out like this. So we have 1/10 of an inch. We have 1 inch right here, which has 10 to the 8 molecules. Each of those molecules can take this much force. And we have, and then we're going to multiply it by 10 to the 7, because that's how many molecules we have in this direction. That distance away, the radius is 0.1 inch. Yeah, the radius we're going to say is, the diameter is 0.2, the radius is 0.1. And so let's see if this even makes sense. So the torque due to these molecules are going to be the shear on them times the we're just going to unwrap all the molecules and say they're a distance of r away, which is 0.1. So it's all the shear times the radius, and that value has to equal 10 to the 3. So let's see if we even did this. So the radius is 10 to the -1. In an inch here, we have an area of 10 to the 8 by 10 to the 7. Oh, my gut's ready to explode. Okay, and it looks like we're not. Oh yeah. And then each of those molecules. So that's how many molecules of interaction that we have that are torquing this distance. So this is adding up to the force. This isn't a force yet. This is just the number of molecules. The force is 10 to the -11. And now we're good to go. So we have 10 to the -11 times 10 to the -1. That's 10 to the -12. And now we have 10 to the -12. 8 times 7. Oh, hell yeah. This is brilliant. You know, this is G-level stuff. So we have 10 to the 8, 10 to the 7. This is 10 to the 15. 15 and 12. Let's do our rinky-dink way to subtract numbers. So I have 10 and -12. I'm going to get a positive number. I'm going to say 12 and 15 are on a number line. I'm going to jack this one down to 10. And then I'm going to bring this one down by 2, so we get 10 and 13. The difference between those is 3, and we get 10 to the 3. And guess what the hell 10 to the 3 is? It's 1,000 pounds. So I think we can totally clean this up, but I feel like I'm the only one that is taking material mechanics down to just being like, hey, like it's no-brainer that you're still dealing with physical elements. These are iron atoms. You know what I mean? It's not quantum level stuff. It's just the fact that, hey, this is kind of the lowest denominator, and it's easy to even work with because you can actually quantify a number. 10 to the 24 isn't that big of a number to work with. You know what I mean? A lot of these physical numbers, they're small and big, but not that big of a deal. And so, hell yeah. So we just did that, and we knew that, we got to the point that if we made our cylinder with just atoms on the outside, like you ain't getting very much juice at all. You know what I mean? So we're going to have 10 to the 5. 10 to the 5 was 10 to the 8 times 10 to the 8 times 10 to the 8. So 10 to the 5 was related to 10 to the 24. So if I had 10 to the 24 atoms in an inch, that's what we were just approximating. Oh, that's the other thing. This whole approximation came off the idea that 1 inch of steel was 1 mole. And so who the hell knows? I mean, Avogadro's number could be 100. We thought steel was 90. Did I get that right? But literally, that's a quarter pound, and a quarter pound is 100 grams approximately. So 90 and 100. So we even did a pretty good job of there. But that's where this whole calculation came from, was on Avogadro's number. We got to use cube root, which is also good. I think I should just stop talking because we're not getting anywhere better. But no, we did it, and we're just kind of double checking what the hell we did. But I think my brain is absolutely fried. Booyah, look at that. We're back to this. And but that really shows the idea that you can shear the outer surface. Cool. The inner surface is shearing, but not as much. If the inner surface is shearing, but not as much, there's not much tension. There's not much shear force on there. And if there's not much shear force, two things add up. There's not much shear, and the distance away from the center is small. And so both those things add up to being like the center ain't doing crap, and the outside is doing everything. If the outside gets more than that angle, you deformed it. And so that's what we have. And it brings up this idea that we bring up the stresses involved. And I hate that, because we just talked about molecules that can only take a certain distance and can only take a certain force. And what we did was just saying, hey, we're going to keep this real simple. Axial tension, 2 molecules, we can pull that way and that way. In shear, we got 4 molecules, and we're essentially pulling that way and that way. And we're just going to say, hey, that's almost just like pulling 2 axially. So that was the assumption that we made, and we're probably in the ballpark. We can't be off by a factor of 10, and we're probably only off, or we're probably either exactly right or off by a factor of 2. So hell yeah. All right, I'm going to be done. Thanks for joining me. But yeah, this shear, I hate this term. The shear stress. I'm sorry, stress. The stress term makes absolutely no sense. If I have 2 molecules and I compress in on them, and you're swimming in a swimming pool between those 2 molecules, let's say you go like a quantum level size and stuff like that, hey, now you're going to be all pressurized. You know what I mean? That's a pressure. But where the hell is the pressure when and the pressure is in between that face. So what we do here is, like, if I pull up on this, maybe I'll answer my own question, and pull up on this, like, and now you're just a molecular level guy, and then you squeeze yourself in between those. Well, one half of your body is going to get stretched, Armstrong, that way, and the other half is going to get that way. And guess what? We're going to call that a pressure. You know what I mean? This is pressure getting pushed together. Or you could have a pressure pulling you apart. You know what I mean? And I think you can imagine that. Even though we think of pressure as like, hey, going into the bottom of the ocean, getting pressurized, but you could also go into space and get pressurized the other direction, where just everything pops out of your face. But, well, what the hell? So we're saying pressure is getting stretched, you know, like one half of your body is going that way, one half is going that way. We're also going to say that's pressure, because we have a force, that's the shear force, and we have some sort of area. Just as if I apply this crunching force, I'm applying a force over your area. And it depends. If you make that area bigger, hey, you might be able to survive it. You know what I mean? If I take this load and distribute it over every aspect of your body, hey, you might be able to survive it. Same if I'm putting you in a vacuum and you're you know, like all the force isn't directly out of your eyeballs. That would suck. But if you could distribute that force over your body, then hell yeah, you can resist that. So the same thing applies to this idea of sideways force. Like, hey, your body is going to get pulled this way and this way, and you're trying to resist it. If all that force this way and this way is on your big toe, sayonara big toe. But if you actually put a duct tape, like a curtain, on your front, you know what I mean? Let's say you skivvied down and attach it to your skin, and then, you know what I mean, someone's yanking on it like that because you're, I don't know, Guinness Book of weird records, and then someone's pulling down on the other duct tape skirt that's duct taped to your backside. Well, now, and let's say it's the same force. One was the force that was going to rip off your toe. Your toe's going that way, your toe's going that way. Sayonara toe. Same force is now being duct taped to this entire part of your body. The other force is being duct taped to that part of your body. Well, now what we say is the pressure, the PSI, is much less. And you can withstand this. So the lower the number, and let's say, the duct tape is still attached to your toe. A little bit of that duct tape is attached to your toe. So let's say still we can increase this force to where your toe still pops off. Okay, that number that pops off your toe when we do this weird experiment of duct tape curtains to your front side and back side, that pressure, the force divided by the area of the duct tape on your skin, is going to be the same number, force per area. So that force is going to be way larger in this Guinness experiment. But the area is also way larger, and that ratio is going to be, a number that pops off your toe. So then if we just go to your toe and apply some, maybe some super glue, on a little piece of fabric, and then also pull the other way, which all we have to do is just pull one way and, put something under your feet. That force is going to be way less. The area that's attached to your toe is also way less, so we have a lower force and then a lower area on your toe. Guess what? That proportion is going to be the same as the other experiment. That is the PSI that rips off your toe in this weird experiment, and this is the PSI required to rip off your toe in just trying to rip off your toe. And so that, at least for me, because that's the other thing, I don't want to just say like something is dumb and we should just like disregard it, but sideways pressure is bizarre as, and we use it, the shear stress, and it's in PSI, but it is not like hydrostatic pressure. So you just really have to be like, hey, this is a special quantity that's useful, but also I think it makes shear painful as well, and you might have to take this class a couple times like I did. But hell yeah, hydrostatic force, like axial and compressive force, I think we get it. This idea of sideways force, it seems ridiculous, and it is a made-up quantity. You know what I mean? So just know that. It's made up. It's a made-up quantity. It's useful, but it's still more useful to be like, hey, this pocket of 4 molecules, and if I pull this way and that way, these 2 molecules are getting farther apart. These are crunching in. I can boil the whole breaking point of this down to axial and compressive forces. And so, and that's why we have the Morse diagram, because any shear force at this 45-degree angle is just axial tension and then compression at the same time. You know what I mean? So shear is kind of a made-up quantity, and it's just like, well, it's almost like the chicken or the egg. Like when I'm compressing a chunk of lumber and it breaks at a 45, did it break in shear? Or did it break because tensile and compressive forces got too much? You know what I mean? It's just like, that's the madness. Because tensile and compressive forces make sense. This whole idea of representing them in a structure, it's a kind of, it seems like one more level of made up. And it makes shear just kind of, and then we're just going to say we're going to quantify this. You know what I mean? Because we have some sort of area that's getting sheared, the area between those 4 molecules. That's the area. That's the force. And, yeah, even though when we have that area is, it seems like a ghost. Because what's actually happening with this, with those 4 molecules, is it's not really representative of the area between those. It's actually representative of the area, these are getting farther apart, it's actually representative of the area between these 2 molecules and the area between those 2. So it's just fascinating that shear can be represented as two different things. It can be represented as this area between them, or it can be looked at what's actually happening. These two molecules are getting farther apart, these two are crunching in, and it's probably the axial, compressive, and tensile areas in between those. So I just think anytime that you can represent something as axial tension or compression kind of makes your mind not bleed. And that's why on the Moore's diagram is like you can always rotate something to where something where the shear forces go away. Shear forces don't exist, and then what you're left with is just axial tension and axial compression, and those directions can be in any four ways. They can either be both in tension, or they can be both in compression, or one or the other. All right, so I think I'm satisfied because I don't know. I think I actually proved to myself that I'm okay with the idea of sideways force. I'm getting a little bit better with that. But at one point, I'm just like, this is garbage. You know what I mean? Especially if it's not even going on. You know what I mean? If it's just a made-up quantity, that's all right. It's all right if you're just observing the universe and being like, hey, I see this representation, and every time I see it, it mimics like what's actually happening. Cool. But is it a property that even makes sense? I don't know. But I guess maybe no property actually makes sense. I don't know. But pulling two things apart and saying, hey, their area is actually I can second guess myself on that. Like if I have two molecules that are just kind of doing their thing, again, there is no such thing as the area between them either. But we represent that as pressure. You know what I mean? You basically just have interactions between mass and electrical charges. And so the area is irrelevant. The area is a manifestation of that this is a three-dimensional object that can only occupy that space, and something else can't occupy that space. So you'd have to have another molecule there and another molecule there, and hence you have a three-dimensional structure that you can measure the area. So hell yeah, I think that is useful to be like, are we just making stuff up, or is it okay? Yeah, so I think I can breathe a little bit easier. Sideways pressure. It's still bizarre, and I'm going to make fun of it because I swear it's what caused me to have to drop out. But doing something a second time is what made me get a passion for this subject. I don't know how to teach it, but I think I'm on the road. So hell yeah. So thanks for joining me on this one. I think we definitely need to be done because all the good stuff at the end was about 20 minutes ago. So thanks for joining me. Hell yeah.